Genetic algorithms for scheduling problems. Genetic algorithms offer a powerful approach to solving complex scheduling problems that traditional methods often struggle with. By mimicking natural selection processes, these algorithms evolve solutions over generations through mechanisms like crossover, mutation, and selection. This makes them particularly effective in scenarios where brute force computation is impractical. Scheduling challenges arise in various domains, from manufacturing to project management, where optimizing resource allocation within constraints is critical. Genetic algorithms provide an adaptive solution framework capable of navigating vast search spaces efficiently. Their ability to handle nonlinear relationships between variables sets them apart from conventional optimization techniques. The evolutionary foundations of genetic algorithms. At their core, genetic algorithms draw inspiration from biological evolution principles first formalized by Charles Darwin. These algorithms model survival of the fittest dynamics using computational representations of potential solutions. The process begins with randomly generated initial populations representing candidate schedules. Each individual in this population contains encoded information about how resources will be allocated across time intervals. Fitness functions evaluate how well each schedule meets predefined objectives such as minimizing delays or maximizing throughput. Individuals with higher fitness scores are more likely to pass on their characteristics to subsequent generations. Crossover combines elements from two parent solutions to create offspring solutions, enabling exploration of new combinations without random guessing. Mutation introduces small random changes to prevent premature convergence and maintain diversity within the population. Selection determines which individuals get to reproduce based on their performance metrics, ensuring quality improvement over time. This iterative refinement continues until either an optimal solution is found or a predetermined number of generations have been processed. The evolutionary metaphor provides both conceptual clarity and practical effectiveness when tackling real-world scheduling complexities. Modeling real-world constraints in schedule optimization. One key advantage of genetic algorithms lies in their flexibility to incorporate diverse constraint types commonly encountered in scheduling applications. Hard constraints represent absolute requirements that must always be satisfied, while soft constraints can be violated at some cost penalty. For example, in workforce scheduling, hard constraints might include labor laws limiting daily working hours, whereas soft constraints could involve preferences for certain shift times. Encoding these rules into the chromosome structure ensures valid solutions emerge naturally during the evolutionary process. Constraint handling techniques. Various strategies exist for integrating constraints into genetic algorithms. One common method involves penalizing invalid solutions by reducing their fitness scores proportionally to violation severity. Another technique uses repair operators that automatically fix violations after generating an initial candidate solution. Hybrid approaches combining penalty-based evaluation with dedicated constraint satisfaction routines often yield superior results. Researchers continue exploring novel ways to balance constraint enforcement with algorithmic efficiency, especially when dealing with high-dimensional problem spaces. Evaluating solution quality through fitness functions. The design of appropriate fitness functions significantly influences the success of genetic algorithm implementations for scheduling tasks. A well-crafted function should accurately reflect organizational priorities while remaining computationally feasible to calculate. In production scheduling contexts, typical objective measures include total completion time, tardiness penalties, machine idle time, and resource utilization rates. Multi-objective formulations allow simultaneous optimization of several conflicting criteria, though they require specialized handling due to non-dominated solution landscapes. Normalization plays a crucial role in comparing different objectives since they often operate on distinct scales. Weighted sum approaches combine normalized values with coefficient weights reflecting relative importance, but may introduce bias depending on parameter choices. Alternative methods like Pareto front analysis enable identifying trade-offs among competing goals without forcing arbitrary prioritizations. Selecting the right evaluation strategy depends heavily on domain-specific requirements and available computational resources. Population initialization strategies for effective search. Initializing a population effectively determines how quickly useful solutions appear during the evolutionary process. Random initialization creates diversity upfront but risks including many unviable candidates requiring extensive refinement later. Heuristic-based seeding leverages existing knowledge about good partial solutions to generate starting points closer to viable regions of the search space. For instance, constructing initial schedules around known efficient patterns improves early-stage feasibility and accelerates convergence. Hybrid approaches that blend randomness with guided heuristics tend to outperform pure randomization. Careful tuning of population size balances exploratory power against computational demands, ensuring sufficient variation exists without overwhelming processing capabilities. Adaptive initialization schemes adjust generation parameters dynamically based on feedback from earlier iterations. These intelligent systems continuously refine their sampling strategies to maximize informative value while maintaining reasonable runtime expectations. Improving convergence with crossover operators. Selecting suitable crossover operators profoundly affects genetic algorithm performance in scheduling contexts. Single-point crossover exchanges segments between parents at fixed positions, preserving local structures while allowing global recombination possibilities. Uniform crossover randomly selects genes from both parents, promoting greater mixing but potentially disrupting beneficial configurations. Specialized crossovers tailored to particular scheduling features can enhance solution quality by respecting temporal dependencies inherent in most sequencing problems. Parameter control techniques determine how frequently different crossover modes apply. Adaptive operators that modify probabilities based on current population diversity help avoid premature convergence while maintaining sufficient exploration capability throughout the search process. Balancing exploitation and exploration remains central to successful implementation. Too much emphasis on preserving existing good traits limits discovery of better alternatives, while excessive experimentation slows down progress toward promising areas. Managing mutation rates for optimal diversity maintenance. Maintaining adequate diversity prevents genetic algorithms from getting stuck in suboptimal regions of the solution landscape. Mutation introduces controlled variability, helping explore previously underrepresented areas while avoiding complete loss of accumulated improvements. Fixed mutation rates work reasonably well for simple problems but fail to account for changing environmental conditions during evolution. Adaptive mutation strategies dynamically adjust perturbation levels based on population homogeneity indicators measured periodically. Some implementations use tournament-based mutation where only the least fit members receive increased mutation chances, focusing disruption efforts where they're most needed. Others employ self-adaptive mutation where chromosomes themselves encode preferred mutation intensities. Research shows that carefully calibrated mutation rates lead to faster convergence without sacrificing final solution quality. Finding the ideal balance requires empirical testing, combined with theoretical analysis of problem characteristics. Enhancing selection mechanisms for better progression. Effective selection mechanisms ensure continued improvement by favoring superior solutions while retaining enough variety to sustain innovation. Roulette wheel selection gives proportional representation to fitter individuals but risks premature dominance by exceptional performers. Tournament selection avoids this issue by pitting small groups against each other, giving less dominant candidates occasional opportunities to propagate their genes. Elitism preserves top-performing solutions explicitly, preventing valuable discoveries from being lost during reproduction phases. Combining different selection pressures at various stages of evolution helps navigate complex optimization terrains. Early generations benefit from broad exploration, while later phases focus increasingly on fine-tuning successful configurations. Dynamic adjustment of selection intensity according to population distribution allows flexible response to emerging trends. Intelligent systems continually monitor diversity metrics to optimize pressure application precisely when needed. Addressing premature convergence challenges. Premature convergence occurs when populations become too similar before reaching true optima, leading to stagnation in solution quality. Several mitigation strategies address this challenge from different angles. Introducing niching techniques encourages maintenance of multiple distinct solution clusters simultaneously. Sharing functions reduce fitness scores of closely related individuals, creating incentives for divergence rather than uniformity. Random restarts periodically reset portions of the population to inject fresh perspectives. Hybridization with other meta-heuristics like simulated annealing or taboo search diversifies the overall search strategy beyond what standard GA alone can achieve. Specialized encoding schemes sometimes prevent early convergence by structuring representation formats in ways that inherently discourage similarity accumulation. These innovations help maintain robustness even in highly constrained environments. Performance metrics for algorithm evaluation. Assessing genetic algorithm effectiveness requires careful measurement of relevant performance indicators. Commonly used metrics include convergence speed, solution quality, and consistency across independent runs. Convergence curves track average fitness progression over generations, showing how rapidly improvements occur. Standard deviation measurements reveal stability of outcomes, indicating whether results depend strongly on initial conditions. Hypervolume indicators quantify multi-objective optimization achievements by measuring volume dominated by obtained solutions. These metrics help compare different approaches fairly despite varying optimization targets. Benchmark comparisons against established solvers establish context for algorithm strengths and weaknesses. Cross-domain evaluations demonstrate generalizability across different scheduling paradigms. Case studies demonstrating practical applications. Real-world deployments highlight genetic algorithms' versatility in addressing varied scheduling needs. In healthcare settings, they optimized nurse rostering considering staff skills, availability, and patient care requirements simultaneously. Aircraft maintenance scheduling benefited from GA-driven optimizations balancing technician expertise with equipment readiness timelines. Production line scheduling saw significant reductions in idle time through smart job sequence arrangements. University timetabling projects successfully integrated course prerequisites, room capacities, and instructor availability constraints using customized genetic algorithm frameworks. All cases showed measurable improvements compared to prior manual or rule-based systems. Ongoing research explores hybrid models combining GAs with machine learning predictions to further enhance scheduling accuracy and responsiveness to dynamic changes. Future directions and emerging trends. Advancements in computing power open exciting avenues for expanding genetic algorithm capabilities. Parallel and distributed implementations accelerate execution speeds dramatically, making larger-scale problems tractable. Integration with artificial intelligence components enables adaptive learning about problem structures, improving efficiency over time. Quantum-inspired variants promise breakthroughs in handling exponentially complex search spaces. Cloud-based platforms facilitate collaborative development of sophisticated scheduling tools accessible globally. Continued interdisciplinary collaboration drives innovation at the intersection of biology, computer science, and operations research. Emerging fields like digital twin technology present new opportunities for applying genetic algorithms in virtual environments mirroring physical realities before implementing actual changes. Conclusion: genetic algorithms prove invaluable for tackling intricate scheduling problems where traditional methods fall short. Their evolutionary foundations provide a robust framework adaptable to numerous industry-specific requirements. To implement successful scheduling solutions, practitioners should focus on thoughtful design of constraint integration, fitness evaluation, and population management strategies. Experimentation with different operator configurations remains essential for achieving optimal results tailored to specific application domains.